Okay, so, well, the recording is starting. Okay, so welcome to this lesson. The aim of the lessons of today is concluding the part concerning the fundamentals of digital circuits. And then we will move also, if I hope we will have time, to the study of the first simple block for realizing sequential circuit. So today we will introduce the dynamical parameters of logic gates. We will discuss how we can realize other logical functions using CMOS technology. We will discuss problems related to power consumption. And then we will move to the sequential circuit parts, starting introducing the concept of flip-flop. So these are the slides that we started in the previous lesson. And in particular, I remind you that last time we have reviewed the MOS transistor concept. And in particular, we have focused on the structure of the CMOS inverter. And finally, we have discussed the static electrical parameters of the NOT logic gate, so of the inverter. And I have introduced the concept of output interface. And we have seen that we have basically 3 different types of interface. I have also uploaded yesterday a list of chapters of the book of electronic system of Neil Storey, where there in those chapters you can read the concept that you should have in your background from system technologies, electronic system technologies and measurements. This book, I believe that you can simplify it on the web. I was told that it's possible also to find directly the PDF file, or you can buy, of course, it. And in case you have a problem in finding the book of any question related to that part, please let me know. Okay. Is there any question concerning the last 2 lessons? May I continue? Yes, please. So if you have a question, I think that you can unmute your microphone and you can speak. Or otherwise you have to...
Hello, Professor. Can you
Hello?
hear me?
Yes, I
Yeah,
do
I
very
have
well.
a question regarding the open drain output interface.
Okay, I will take it.
I realized that the voltage, output voltage, will change if we have a load at the output. So does it somehow affect, the compatibility between the two modules?
Yes. So the question, I repeat the question also for the other students. Just let me find the slides, just to remind you also to the others what we are speaking about. So your colleague is referring to this type of interface, the open drain output. And as I told you last time, the output interface, it is composed only by the NMOS. So as you can see from here, when the NMOS is on, we guarantee in the output node the low state. So we are always sure that we are able to guarantee the low voltage level. The problem, it occurs when, on the contrary, we have to guarantee also the high voltage state, because it's clear that in this condition, since you have nothing here on the top, it is impossible to guarantee a voltage high at this node when the NMOS is an open switch. So, as told you last time, in this case, what we have here the open drain output. This is the output. This is the output of your circuit. And to make it working, you have to add from the outside of the circuit. So you have to take and solder there. This is additional resistor that is defined as the pull-out resistor. So the problem, as your colleague is saying, it's related to the case when we connect a load to this output. Because of course, what it happens that let's assume we have the case when the output must be high. So when this output is high, we know that the MOS is an open switch. Okay, so we have no current flowing toward ground in this direction. So this current is 0. But we have, of course, a current flowing through the pull-up resistor down to ground along this path, so to the load. And as a consequence of this current, we will have a voltage drop here on the pull-up resistor. So the point that your colleague is saying, okay, but if I have this current, I will have a significant voltage drop on the pull-up resistor, and as a consequence of that, this voltage here will be reduced by this voltage drop, and maybe the compatibility is not guaranteed, because I remind you that here the output voltage must be always higher than VOH, or in other words, it must be higher than VIH plus the noise margin. This is the condition to be compatible with the load. If the load is, for example, another gate, let's assume this is a gate with VIH, then we have to guarantee that the voltage in this node here is higher than VIH. Okay, so the point is that when you have a load, you know the current that is flowing in that particular load because it depends on the load, and therefore you will design, so you will choose the value of the pull-up resistor such that VDD minus the pull-up resistor times the current that is required by the load is at least higher than VIH or higher than VOH. So this is a problem concerning the design, the selection of the value of the pull-up resistor. This is a problem that we do not consider in this course. We do not try to solve it, but remind that in case you have to mount a pull-up resistor, you cannot choose any resistor. You have to choose a resistor in a proper range such that this expression is valid. Do I answer? Okay, is there any other question? Other questions? No, it seems there's no other question, and so we can start the new part. Okay, so dynamic parameters. Last time I introduced the concept of dynamics. We refer to dynamics every time we care about the evolution of the voltage at any node of the circuit as function of time. Since transitions are not instantaneous because we always have a transient, an electrical transient, last time I told you that these voltages are not infinitely fast. So for example, we have for the input and output signals, as shown here, we have rise time and falling times, first of all. Then we have delays between input and output. A variation indicated here at the input will cause a variation of the output, but this variation is not instantaneous. We have always a delay between the variation of the input and the variation of the output. In this lesson, we want to understand why we have these delays. Where the question is, where are these delays coming from? Okay, and as consequence of that, we have to study the dynamic behavior of the circuits. This problem is relevant because we would like to have circuits that are very fast. So we would like to make this delay between input and output, of course, as small as possible. But as we will learn today, this delay can be small, but it's not zero. Okay. So first of all, why do we have this delay? The first thing that we must remember, it is that inside the CMOS, we have several different parasitic capacitance. So the MOS behaves as a channel that is controlled as a channel, so is a device that allows a flow of current controlled by the voltage that we apply between the gate and the source. So it is as if we control the flow of water controlling another parameter, that in this case it is the VGS voltage. But also, so there's not only this behavior like a resistor controlled by the gate voltage, but we have inside the structure many additional parasitic capacitance that are there. We can't avoid them. In this figure, in this one, I'm showing you the various contributions to the capacitance. So why we have so many capacitances? Because we have many interface where we have an accumulation on one side of positive charges and on the other side of negative charges that are separated by, for example, the oxide, which is an isolator. So I remind you that we have a capacitor when on one side we have the accumulation of positive charges, on the other side we have the accumulation of negative charges, and here in between we have there's no current. We have isolation. Where are these capacitances? The most important capacitances of the CMOS are those that in this figure I indicate with bold. So the important capacitances are this one, and this one, that I indicate as C, GS, CGB, and CGD. They say for capacitance between gate and source, capacitance between gate and bulk or substrate, and capacitance between gate and drain. So I recommend you, for those who are interested, for example, there's this very nice video that explains you the physical origin of these various capacitances. It's a bit complicated to understand them. So if you're interested, you can have a look. Or just remind that we have these several different capacitances, these are important. Let's see, for example, the physical origins of this capacitance CGS. So what we have here? We have here CGS is the capacitance between the source and the gate. Why? The reason is this one. We already know that the MOS is given by the oxide. Then we have the metallization for the gate contact. Then you have the N plus for substrate and drain. And here we have the P dop substrate, which is sometimes also indicated as body. When we apply, as I told you last time, the voltage between gate and substrate, we accumulate here a certain quantity of charges. But as you can see here in this figure, we have also here the N side. The N side and plus side, it means that there you have electrons as majority carriers. So here you have an accumulation of electrons that overlaps in this narrow region under the oxide. Here you have the accumulation of plus charges because you apply the voltage VGS. And as you can see in this very simple picture, we have here at this interface an accumulation of minus charges and plus charges, which are separated in between by the oxide. So this one, it is a capacitance. It is a parasitic capacitance that we indicate with G capacitance between gate and source. And in an analogous way, we can have a capacitance between the gate and the drain. But also, you can see here that you have the accumulation of charges because you have here the channel. So you have the accumulation of electrons, so of minus charges in the channel, the oxide, and the plus charges in the metal. And also in this case, it turns out that this is a capacitor. In this case, therefore, you have a capacitance, an equivalent capacitance that we indicate as C, between the gate and the body or the substrate. Okay, these three capacitance are quite important to determine the dynamics of these devices. So, in conclusion now, we ask, what do we see if now we look inside the gate in this direction? We know that, for example, we set to ground the substrate, and the substrate is, the source, and the source is at the same potential of the substrate, so source and P substrate are at the same potential. And so it means that if we look in this direction, what do we see? We see an equivalent capacitance that stays between ground and the gate, right? So in conclusion, we can say that if this is a gate, we have in total an equivalent capacitance, C input. So this is the equivalent capacitance that we see looking inside the gate of the MOS. And if we are in static condition, how much is the current entering in the gate? Any idea? Is this current 0 or higher than 0? Is there a gate current? The current is 0. Indeed, if you have a MOS, so this is our gate, this is the source, and this is the drain, this current here, Eg, is always 0 because we cannot have current there because there's the oxide which is isolating in between. So the current is basically 0, but looking in this direction inside the gate, we see an input impedance which is given by this equivalent capacitance. And we indicate this equivalent capacitance as the input capacitance. Okay? Clear? That is physically present because of this physical effect that I briefly summarized here. Okay? This is for what happens for one MOS. Okay? What does it happen if now we have the inverter? If now we have the inverter, I remind you that the structure of this inverter is given by two transistors. These two transistors, they have the same, they share the same gate, right? So if I indicate with Cg the gate capacitance of one MOS, how much is the input capacitance? Now we have two MOS. It's the parallel of the two. Why? Because this one, okay, if we look at the NMOS, as we learn, the NMOS, if we look here in this direction, we see an equivalent capacitance Cg, and this is the equivalent capacitance of the NMOS. But then you have the same for the PMOS. Then you have to add another equivalent capacitance, Cg, for the PMOS. So in total, you have the parallel of two capacitors. So in this case, the input capacitance, it is 2 times Cg. If we assume that the capacitance, the parasitic capacitance of the P is almost equal to the parasitic capacitance of the N. Okay? So in conclusion, we learned that if now I stay here and I look in this direction, I can also plot an equivalent circuit for the input of this gate of the inverter. How is this equivalent circuit? This equivalent circuit is given by the input capacitance C input that we just learned that in the case of the inverter, it is the parallel of the two gate capacitance. And if we want to be very precise, we can add in parallel an input resistance. But as we already mentioned, we already know that the static current entering here, this current is basically zero because the gate current is zero. So we can say this one is an open circuit. Actually, there's a resistance there, but that one is extremely high. And so we say, now this resistance, it's infinite, and we can neglect it. The important point is that whereas we can neglect the input resistance, the input capacitance cannot be neglected. Clear? So in conclusion of this understanding, we can say that the equivalent input impedance of the CMOS is given basically by the sum of the two capacitances of the gate of the N and of the PMOS. And if we look in this direction, so this is the gate, the input node, we can say that we will see only the input capacitance connected to ground. Okay, so now the question is, what happens during the transient when we connect two modules? Let's see this example. We have a module A, which is, to simplify, an inverter that is connected to module 1, which is another inverter. Let's assume that the input of A, so this voltage here, is initially set to high, so it's very close to VDD. So there's a question, can you explain why are these capacitance bad for us? They are bad because they are the cause of the delay. So this, I will show you now that these capacitance are bad because they cause the delay in the circuit. As mentioned you at the beginning, where is that? It was this line. We have a delay between a variation of the input and the variation of the output voltage. I will demonstrate you now that this delay is caused by this capacitance. And this is the demonstration we are starting now. So let's imagine this experiment. I switch the input voltage from high to low at time instant t equals 0. The question is, what does it happen to the output voltage here, VB? The question is this output voltage VB instantaneous? So this is an inverter. If it is an ideal inverter, VB should be something like that. No, I plot it in red because VB is red. So VB should be something like that. An instantaneous variation of the input makes an instantaneous variation of the output. This is not true. And what we want to do now is calculate VB as function of time. Okay. What can we do for doing that? So for doing that, so our purpose now is calculating this VB as function of time. For doing that, we have to simplify the problem. To simplify this problem, we make use of equivalent circuits, the one that learned in the last lesson. Equivalent circuit for the output of A and for the input of B. So let's plot now the equivalent circuit for the output of A. So the equivalent circuit for the output of A, it is the equivalent circuit for a totem pole output. This is the output resistance for the PMOS. Then we have a switch. Then we have the output here. Then we have another switch. And then we have the output equivalent resistance for the NMOS. This was ROH, this is ROL. We then assume that ROH is equal to ROH is equal to R output. The assumption, the hypothesis that we make now, it is at the initial condition, we have that the input is I. So we start, I cancel this one because this is not true. We start with the input voltage to be high. If the input voltage is high, the output is low. So in our initial condition, we have that this switch is open. This is our initial condition because the output is low and the input is high. Then at the time instant t equals 0, so here in this point now, what we have? We have a switch, instantaneous switch of the input. Okay, so it means that the input, boom, go to ground to 0. Therefore, we assume that instantaneously this switch closes and this switch open. And we assume that this is instantaneous, right? We neglect the transient of the commutation of the MOS because this transient is extremely fast and therefore it can be negligible, right? Now, if I close this switch, if now I close this switch and here I have the second inverter, I have to substitute what I see looking in this direction. So I replace in the equivalent circuit the block B with its input capacitance. This is the input capacitance of the digital block B. Okay? What happens? It happens that when I closed this switch, okay, let's repeat again. In the initial condition, at t equals 0, we started with initial condition like that. In this initial condition like that, how much is the voltage here? I remind you that this node is B, right? VB at t equals 0, how much is it? Looking at this circuit. If I have this circuit and it's a 0 volt. So I start at the initial condition T0 minus, so before the switch, that the voltage here is basically 0 volt. So the capacitor is completely discharged. Okay? Then at T0 plus, so an instant after the switch of the input, I change the condition. I open this one and instantaneously close this one. So what we have, if I make this switch, the voltage here is 0, the voltage here is VDD, and so I have 0 here, VDD here, I will have a voltage drop on this resistor, ROH. And therefore, I will have a current that starts from VDD, flows through the equivalent output resistance RO and enters in the capacitor. So I have a current charging this input capacitance. And therefore, with time, I will have a transient. So this voltage, the output voltage, VB, which corresponds to the output voltage of A, will change with time with a transient. This transient, you recognize, it is the transient of which type of circuit? Which is the circuit that you recognize here? An RC circuit, yes. You recognize that immediately after the switch, I have an RC circuit. Indeed, I have a voltage source, which is VDD, a resistor, which is RO, and a capacitor, which is C input, with the initial condition that is VB at 0 minus of about 0 volt. Okay? So I have to plot now the voltage VBT as function of time. This is reported in these slides. So this slide is showing what I just told you now. And then we have now to plot the voltage VBT. So if we go back to this circuit, can you explain at least in a qualitative way how does the transient of VBT look like? What we expect? If I ask you, let's plot now VBT. So the question is, let's plot as function of time VBT. Is it increasing linearly? Is the transient linear, so it's just a straight line? No, it's not linear, it's exponential. So the transient for VBT, it is this one. I start, this is 0, t equals 0. At t less than 0, we assume that VB is very close to 0 volt. At t infinite, when the transient is concluded, how much is the voltage that I will eventually reach? Let's go back to this circuit. At t going to infinite, I will reach VDD. So I basically start from 0, and at t to infinite, I will reach VDD. In between, I have this transient, which is the transient of a first order RC circuit. Okay? It's a decreasing exponential transient. It's decreasing exponential because this shape, if you look reverse, it is the exponential which is decreasing. This difference, this one, is decreasing in an exponential matter. Okay? How much is the time constant of this exponential, the tau? The tau is equal, in our case, to the product of the capacitance times the resistance. We see that the capacitance, the resistance is the equivalent output resistance of module A, and the capacitance, it is the input resistance, the input capacitance of module B. So the tau, it is Rho times C input. Okay? This time constant, it is basically the slope of this line, right? That is a measure of how fast the exponential decreases. So if tau is very small, I will have a very fast transient. So for example, something like that. If tau is big, the transient will be very, 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 very long. Okay, clear? Is it clear? Good. So now the question is, let's remember the original problem. So now we have realized that the input, the equivalent input capacitance, so those parasitic capacitance of the MOS, makes this transient longer or shorter depending on its value. Okay, so the question now is, if now I am module B, I am this yellow guy, when I recognize that the input voltage in module B is I, remember that now during this transient, I see that this voltage, which is the input voltage in B, is not constant with time, but it is increasing with time. The question is, when does B recognize its input as an I logic state? How would you answer to this question? Look into here. Any idea? Try to guess. Yes, the answer is correct. When the voltage VBT reaches VIH, so if I set here this level VIH, I see that, for example, if I take the red transient, I'm at this point. I see that now the input voltage in B, that is the red curve, is recognized as high. Clear? So from this time instant on, I say the output of A is high. Okay? And you see that there's a delay that we call TD, T delay, or someone TP, propagation delay. It's the same stuff. So you see that you have a switch of the input. Let's go back to the original problem. We have a switch of this voltage. This voltage here switches from high to low at this time instant t equals 0. Then the voltage here, it will switch from low to high, but not at t equals 0. It will switch later on when this one is higher than VIH. And we measure this one as the delay. Okay, then I will answer to all of your questions. So what I wanted to show it is that the fact that I have an input capacitance, it is the origin of this delay. And as consequence, I would like to have this delay as small as possible. Now I will answer all the questions. Let me see the question on the chat. Just a second. So there's a first question from Gabriele. So to reduce delay, we use either a smaller RC or a VDD greater than VIH. Okay. This question, it is interesting, but it's also incorrect. There's a mistake in this question. Do you recognize it? First of all, can you see the mistake? Anyone can find the mistake of Gabriele? What is wrong is that you can't say that you have to use VDD greater than VIH, because by definition, VDD it's always higher than VIH, because by definition, VDD, it is the highest voltage that you have in the circuit. Any higher voltage, it is always lower than VDD. Okay, so by definition, VDD is always higher than everything. It's the highest voltage that you can have in the circuit. And therefore, all the rest, input and output, are always smaller. Clear? And this was the wrong part of your question. The first part, it is an interesting part, because if you want to have fast circuits, and we will discuss this in this lesson, what you have to do, it is reducing, for example, this time constant. So a fast circuit should have or small output resistance or a small input capacitance. Do I answer, Gabriele? Was this your question? Okay, then there's another question. Sorry, it's a bit complicated to scroll. Just a second to scroll through the questions. Then there's a question from Giacomo Zanella, but doesn't this mean we are inputting forbidden voltage levels at the inverter input while the capacitance reaches VDD? Yes, it doesn't mean that you're inputting forbidden. It means that you have a transient, as shown here. So you have this time range, this interval, which is an interval where voltages are neither high, neither low. So it means that in that time interval, the voltage, it is a voltage that it does not identify any state. We can only say that after this delay, TD, we are sure that the output voltage is high. Okay? During this time range, the gate that follows, it does not see an high voltage. Actually, then there's a question concerning the value of the input. The value of the input capacitance, it's generally the sum of all. Sometimes it's dominated by CGS. Okay, other new, okay. Good. So all this stuff is explained in these other slides. Typically, you can use, okay, so to calculate the delay, you should write the analytic expression of this decreasing exponential transient and set when the decreasing exponential is equal to VIH and to calculate the P. If you do that, you can end up with analytical expressions that very often they are approximated with a rule of thumb. So typically the rule of thumb is this one. This delay TD is approximately equal to the quantity 0.69 times the time constant. So if it is required to calculate the delay, you can simply take this constant value that is almost always the same, so about 0.7 times the time constant of the transient. And this is a good expression for evaluating the delay in a fast way. So as shown here, we can say that we can approximate the delay, and in this case, it is the delay for a transition of the output that is from low to high state. So this is the delay for the transition from low to high state. If you repeat the same story, and it's all explained here, if you repeat the same story, you have also the transient for the opposite transition. So for the transition from from high to low state. Let's understand what happens now. Let's assume now we have the opposite condition. Let's repeat once more all the story, but in the opposite case. Let's assume that at T0 minus, we have that the input voltage is low, right? So this is the input voltage to the inverter, and we assume that initially it is low. This means that the output, VB, it is high. So we start in an initial condition with the output, so with this node directly connected to VDD, right? This is our initial condition. So in this case, we start with VB at T0 minus equal to VDD. In other words, we start with initial condition where the capacitor C input is completely charged. Before we started with the capacitor that was discharged. Now we start with the capacitor charge, so it means we have all the accumulation of positive charges here, right? So what does it happen now? At T equals 0 plus, V input goes high, and so we make the PMOS on, so we switch on the connection to ground, and we make the NMOS off. So we open the connection to VDD. So in this case, what we have, which type of transient we have? What do you expect to see? Yeah, the transient now it is the opposite. We have the discharge of the capacitor. So you have the discharge of the capacitor through a current that is flowing. So this is the discharging current that is flowing from the capacitor node down to ground through the equivalent resistance of the NMOS. So in this case, the situation is this one. If we plot the voltage VBT as function of time, we will start at t equals 0. At t0 minus, this voltage is high, set to VDD because the capacitor is charged. Then the voltage in B will start decreasing. So we have this discharging exponential. Then what we have? When module B, when does module B recognize this voltage as low? When the input voltage in B is recognized as a low voltage level? You have to compare the voltage in B with what? Yes, VIL. So we will have in this case that when the voltage in B gets smaller than VIL, for example here, B say, oh, okay, thank you, I understand that the input now is a low voltage level. And again, you have a delay. This delay now, it is a delay for a transition of the output from high level to low level. And in this case, this delay can be well approximated with 0.69 ROL times the time constant of the transient. Okay? And it's reported, everything it is explained here in this slide. And also in this slide and in this one. Okay? Is this clear? Any questions? Is clear? Is it clear for all? Can repeat what? Okay, how you find the time delay? The time delay you have to calculate. So I tell you what one should do in theory, and then I will tell you what you have to do at the exam in practice, okay? So in theory, you have to plot the voltage input at the input node of the yellow node as function of time, solving the RC transient, and you write the analytical expression for this voltage, and then you have to compare it with the input voltage level, high or low, depending if you want, depending on the transient, if it is a transient in the output from a state high to low or vice versa, okay? This calculation, however, is not requested to you. You, I mean, students in applied electronics of computer engineering. I tell you that if you do that, the final result, it will be always an expression where this delay can be roughly approximated with this formula. So at the exam, if I ask you to calculate the delays, you have only to plot the equivalent circuits and then evaluate the time constant of the equivalent circuit. So this is the time constant of the equivalent circuit. And then you have always to multiply this time constant by 0.69. Clear? Do I answer you? Okay. So looking at this expression of the delay, this one that we have just seen now, you can see that the delay is function of the input capacitance, so on the capacitance that we see looking in the direction of the input modules, and of the equivalent output resistance. So what follows? It follows a very important thing that is reported here, the effect of the load. This figure is showing you now what it happens when we have many loads, many other digital modules connected to the same output. So in this example, we have module A and the output of module A, which is this node B, it is connected not just to one module, module 1, but it is connected to several other modules. In this example, we have two yellow modules, module 1 and module 2, which are connected to B. So if now in this case we have to evaluate the delay, how much is this delay? If I ask you, calculate in this case the delay, TD, for example, for a low to high transition, how much is this delay? Guess. No, it's not the maximum. You have to remember the method. You have to plot the equivalent output of A. So if we have a low to high transition, the equivalent output of A, which is ROH connected to VDD, and this is the equivalent output in this direction. And then we have to plot the equivalent input. You see that we have one gate here. So we introduce the one input capacitance, C input of module 1. Then we have another one here. Then it means that you add another capacitance, which is the input capacitance of 2. If you add here another module, for example, if you add here module 3, you would add another input capacitance, that is the input capacitance of module 3, and so on and so forth. So you see that the input capacitance of each module goes in parallel to the input capacitance of all of the others. So in conclusion, here at this node, you see a total impedance, which is the parallel of the input capacitance of each module. In particular, in this case, if you have two capacitors, you have to sum the two capacitors. If you have 3, 4, and so on. So in total, you have that in this case, the delay, it is 0.69 times ROH times the sum from 1 to n, if we connect n modules, of the input capacitance, C input, no, let's use this index n, the input capacitance of each n module n. Okay, clear? So in total, if we assume that the input capacitance of module 1 is equal to the input capacitance of module 2 is equal to the input capacitance of module 3. So if I assume that C input is all the capacitances are the same, I see that the total delay, for example, from low to high transition, it is equal to 0.69, and the number of modules connected times the output resistance of A. So in conclusion, what I see that if I connect many modules at the same node, I make all the circuits slow because the delay scales, increases with the number of modules connected. Okay? So if for some reason I want that this quantity to stay smaller than a T maximum that is given by the specification of my design, let's assume in my design I need for some reason that the maximum delay must stay lower, let's say, than 1 nanosecond. What I conclude from here? What's your conclusion? If in my design, for the speed of the exchange of the information in my circuit, I say, okay, the requirement of my design, it is that all the delays must be smaller than 1 nanosecond, for example. What do you conclude? Looking at this formula here. Yeah, I conclude that I can't connect too many gates. So in conclusion, I conclude from here that if the delay must stay below a specified maximum value, then n is limited to a maximum number of gates that I can connect. Okay? So if you reverse this expression, you will find that n must be smaller than the maximum divided by 0.69 times ROH. This maximum number of gates that can be connected is defined as the fan-out. Yes, a student is saying, is this the fan-out? Yes, it is. So we learned that the fan-out, the maximum number of gates that I can connect, is determined, is caused by the requirement of the speed. And indeed, here you have the definition of the fan-out. Then, given this, you must be careful. So, for example, sometimes, okay, so this concludes the definition of fan-out. Then, for example, if you make a connection like this one, so you want to connect two modules together, and you want to enable or disable the connection, you can use a switch. Okay, so for example, I want module A connected or not connected by module B. Okay, and you want to close this switch when you have these two connected, or you want to open this switch when you want these two not connected. This switch, of course, is controlled by another additional command. So you have the switch command closing and opening this switch. In digital electronics, as you already learned, the switch, so the circuit that makes the switch controlled by a voltage, it is realized with a MOS transistor. So this switch, sorry, it's not a nice, I repeat it. So if you want to realize a switch like this between two nodes, and you want this switch to be controlled by an additional command, an additional voltage that is controlling the switch, you use a transistor, a MOS, connected between the two nodes. This is node 1 and this is node 2. And you apply this, the control voltage. So you apply a voltage to this gate of the MOS, and this is the switch control voltage. When this switch control voltage is high, the switch is on, so it's closed. When the control voltage is low, the switch is open. So via the voltage you apply to the gate of this transistor, you open and closes the switch. The transistor used in this way is defined as pass gate transistor. So we can use a pass gate transistor to connect two gates together. It could be a good idea, but the point is that you should not exaggerate, because remember that also in this case, every time you add this additional device in between, you add resistance and capacitance. This resistance, it is the on resistance when the transistor is closed. This capacitance Cp, it is the capacitance between the gate and the bulb. Okay. So you must remember that you add, in this case, additional capacitance in parent and an additional resistance in input. So in this case, for example, if I ask you to calculate the delay for low to high transition between voltage for the voltage here in C when the switch closes, how much is this delay when the switch is closed? How much now is the time constant of this circuit? Guess? Yeah, it's not completely correct. It's not exactly like this. No, I would say it's wrong. Berk answer is wrong. Try another one. It's better. Yes, it's going to be better, but not yet fully okay. Try again. Not yet. Make the union of the two. Yes, this is the correct one. So how you answer this question? For those, this is the last time I repeat it, then we move to another. You have to plot the equivalent output circuit for A. Then now you have to add the equivalent circuit for the pass gate. And then you have to add the input capacitance of the module B. So now you have that the time constant is Rho plus Ron, because you see these two are in series, times Cp plus C input, because as you see these two are in parallel. So in conclusion, the delay for low to high transition, for example, it is 0.69 times the time constant. Okay, so the last answer is the correct one. Good. Okay, we skip these slides. Another important point, so to make the circuit fast, we have some tricks. Which are these tricks? As we learned today, we have to reduce, first of all, the delay. A reduction of the delay, it means that you have to realize circuits with low output resistances and low input capacitance. And this is demanded to that technology we are using. So to the technology, to the fabrication of the MOS. Okay, this is one possibility. The other possibility, which is the other possibility, it is that if you want to be fast, and this is, for example, the transient of VB, of course, if you have to start from here and you have to reach VDD, which is rather high, it will take a long time because the excursion between ground and VDD, which is, for example, 5 volt, it is very large. And also we know that VIH, it is a voltage which is quite large because it is rather close to VDD. Okay? If you realize a logic, so if you rely on a logic family where VDD is reduced, so if you rely on another technology which makes transistors with a smaller threshold, what will you have? You will have that, for example, in this case, your transient will be much faster, because if now, instead of going to a VDD that was 5 volt, you only go to a VDD which is only, for example, 1 point something volt. And in this case, you see it's faster. Oh, sorry, no. I repeat it again because this plot is wrong. I have to cancel the red line because it's wrong. So if now we start from 0, so the transient, the black transient was this one. If now we rely on another technology with a smaller VDD, you see you will reach you will reach the VDD faster because the excursion between ground and the high state, it is reduced. Okay, so a method for making circuit faster, it is reducing the voltage supply VDD. Okay, however, you have an additional problem, that is the fact that the separation between a low voltage level and a high voltage level is very reduced. So maybe you have problems if there's too much noise, because it might be difficult to discriminate if the voltage is low or the voltage is high. So which are the trends in the technology as reported here? First of all, to make a circuit faster, you need to reduce all the parasitic effect. Okay, so reduce the connectors, which means communication respect to parallel communication. We will return to this problem. Another method for making circuit fast, it is reducing the voltage supply. So to work at lower VDD. as we learn. Another solution, it is using, instead of the logic we have seen till now, another type of logic, which is defined as a differential signal or differential logic. Yes, it's actually a principle which is very much used in microcontrollers. Differential logic, what means? It means that instead of coding the state with a voltage high or low, because we said, okay, we decide that 0 is voltage 0, high 1, bit equal to 1, it is voltage high. But I can use another method. For example, say if I have is positive, then this is a 1. If this differential voltage is negative, then this is a 0. So what I have to read, it's not the single-ended voltage, but the differential voltage, in the sense that if I have two wires, I have the voltage here that I indicate as V plus, the voltage on the other wire that I indicate with V minus, but what I read now, it is Vd as the difference between V plus and V minus. If this difference is positive, it will be a 1. If this difference is negative, for example, it will be a 0. And in this case, it's simpler in terms of speed, because I have only to make little variation of this differential voltage to recognize it. And this is what is called differential logic or differential logic signaling. Okay? Good. So here, this is the end of this very long lesson, which is lesson B1. It was rather long because it is a long introduction to digital electronics. Here you can see the important key points you must return from this lesson and you have to know for the exam. Now we are going to have a break. After the break, we will start a new lesson, which is the next lesson, lesson B2. You have already these slides because I gave you this slide 1 week ago. No, sorry, no. I made a mistake. Sorry. We have to continue. Lesson B1 is not finished yet, because we have to move to the last part, which is how we can realize more complicated combinational logic function using CMOS switches. Okay, let's have 10 minutes break, and we will restart again at 16:10. Okay, if you have question, you can turn on your microphone or write in the chat. Okay, good. So in the second part of the lesson, we will see circuits for the realization of, let's say, a bit more complicated combinational logic functions. And in particular, we will start on how we can realize NAND and NOR gates using the CMOS switches. So combinational logic function and circuit. So as mentioned at the beginning of the in the last week, the difference between combinational logic circuit and sequential logic circuit, it is the fact that in a combinational logic circuit, the output, in this case output is indicated with letter U, the output is a function that can be like, even complicated function of the input logic states at the same time instant t1. The output at time I read the inputs at time instant t1, and the output is a combinational logic function of this input. In a sequential circuit, we have that the output is at time instant t1. It is again a combinational logic function of the input states as in a combinational logic circuit, but also it is a function of the states registered in the previous time instance. So the time is in the past. And for this case, for doing that, we require a memory element. In lesson B2, this is the topic of lesson B2, we will see that this memory element, it is the flip-flop. In this lesson, we focus, on the contrary, on this first part here. And we ask, using just the two very simple ingredients, PMOS and NMOS transistor, how shall we realize generic combinational logic functions? So generic combinational logic function, as you know, these are the combination of simple logic operation. The logic operator are the NOT, and we know we can realize the NOT function using the totem pole configuration of the two NMOS and PMOS, the AND, the OR, and the XOR operation. The inverter is this one. We already studied it in detail. And now we want, using the same principle as before, we learned for the inverter, we want to realize the CMOS version of the NAND gate. So this is the NAND gate, and using a combination of N switches and P switches, we want to realize this NAND operation. In this example, it is the NAND of two inputs that are I1 and I2. Here, this one, you recognize this one, it is the truth table for the NAND. What we see? We see that the output is low for just one particular case. So we have that the output is low when both inputs are I1 and I2 are I. So given this tip, how you would arrange the switches controlled by the inputs to realize a NAND function? Any idea? Could you try to guess? So it means that when both inputs are high, I must guarantee the connection to ground. So if I have one NMOS controlled by I1 and one NMOS controlled by the input R2, these two NMOS must be both connected to ground. So it means that concerning the NMOS, I have one NMOS which is controlled by the input I1, and I have another NMOS which is controlled by the input I2. So you see that in this case, if both inputs are I, we have that these two MOS are both on, and as consequence, the No, it's sorry to say that both must be sorry, I have to. When I say that both must be high to have a connection to ground, it means that they have to be in series, right? Because to be sure that this output here is 0, both of them must be switched close. So in this case, the NMOS are in series. I see that to have an output high, I just need one of the input to be high. So it means that for the PMOS that guarantee the high state, so the connection to VDD, the PMOS are in parallel. One is connected, is controlled by the input I1, and the other one is controlled by the input I2. So this input, it goes to this node and to this node. This other input, it is to this node and to this node. So these are connected together, and these two, of course, are connected together. And indeed, we have that we need both PMOS open and just one PMOS closed to guarantee the output I. So the conclusion is that the NAND function is obtained by NMOS that are connected in series and PMOS that are connected in parallel. Clear? Is this clear for all? Questions? Do you hear me?
Excuse me, can you hear me?
Yes?
Okay, so I had a question. I understand the solution. I mean, it makes sense that the two, so when just one of the two inputs is low, then the output is going to be high. And then if both inputs are high, then the output is going to be low. Okay. But my question was, what if we only wanted to use the NMOS switches? Then could we use an inverter to invert? Yeah, no, okay, not in parallel, not in.
No.
Okay, okay, I see it now.
Yeah.
Okay, thank you. Sorry.
And you can repeat the vice versa for the NOR. So for the NOR case, as you can see, we have the opposite. For the NOR, this is the symbol of the NOR gate. This is the truth table. You recognize that the output is 1 only for the case with 2 inputs too low. All the other cases, it gives an output too low. So it means that we have the opposite configuration. We have to guarantee the connection to the high state when the voltage is low. I remind you that when the voltage is low, we turn on the PMOS. So it means that in this case now, we have that the PMOS must stay in series, as it's shown here, and the NMOS must stay in parallel. So you recognize here that the trick it is first you decide, for example, you start for the connection to ground. So you ask to yourself, which is the configuration of the NMOS to guarantee the output low. And you build up with NMOS in parallel or in series, you build up the connection to ground. The connection on the top, so the PMOS part, it is a complementary. If you have the NMOS in parallel, on the top it goes in series and vice versa. Clear? Let's see an example. We want to realize this logic function. This logic function is, this is a generic, we want to realize now a generic combinational logic function. In this case, the combinational logic function we want to realize is this one. The output is C naught or A naught and B naught, as shown here. And the question is, how do we arrange NMOS and PMOS to realize this logic function? So for doing this, you can proceed by step. And the procedure, it is summarized here in the bottom of this slide. So first of all, we decide to start from the NMOS block. So we decide to arrange first all the MOS transistors here. To do that, we ask to ourselves, when is the output low? We answer to this question negating the output. So we have to write first the not of our combinational logic function. So the not of this combinational logic function, you recognize it out not, it is equal to C and A or B. When we make this true, it means that our output here will be 0. So what it means? It means that the output will be low if we have C connected to ground, and because here you have, let me write again. So the output not, it is C and A or B. You can read it as we have the output low when C is low and quindi C is low and we have that A or B are low. Okay? So what it means? It means that to be sure that we have the output low, we have to guarantee the connection to ground via the NMOS, which is controlled by C. And so we have a second part that must stay in series because they together must be switches closed, and A or B. So we have other two MOS, a NMOS controlled by A, and another one controlled by B, and these are in parallel because you can see that we will guarantee this output here, this is our output, here to low if this switch is closed and at the same time this switch or this switch are closed, or also both together. So in this case, we can sketch the bottom part of the circuit. Now, after that, you sketch the bottom part of the circuit, which is this one. So this is the bottom part we just sketched. Okay, with these two in parallel. Now you have to plot the top part. The top part, it is the complementary part. What on the bottom, what on the bottom it is in series goes in parallel and vice versa. So now these two are in parallel, and in the PMOS part, they go in series. C, it is here in series, and then it goes in parallel. So we have here another node. This is P. Okay, clear? And in conclusion, the circuit is shown in this part. So you see that here you have the P, A, B, which are in series in parallel to the C. Here you have A, B in parallel, which goes in series to the C. Okay, I think there was a problem with the connection. Do you hear me now? Okay. I think I have to share again the slides. Do you see now the slides? But unfortunately, okay. Okay. So was this part clear? Could you at least understand that? Any feedback from the others? Okay, yeah, it's not complicated. I think that if you you revise that, it will work. Good. So this was an example to show you how you can realize this function. This is another example, so of now realization of the multiplexer function. So the multiplexer, what is it? A multiplexer, it is the control of an output by a additional control signal. So for example, we have in this example an output U, and we want to send to this output U or the signal A or the signal B, okay? And we decide with an additional control signal, which is S. For example, if S is 1, we want to connect, we want to close this switch. So we want to set the output equal to A. If S is low, we want to output B. The multiplexer can be simply realized using the pass transistor, the pass gate, as we've seen before. So it means that this switch and this one, these are complementary switch, because when one is closed, the other has to be open, and vice versa. And you can use for this switch a NMOS in parallel here with a PMOS. You see that when S is high, the NMOS is closed and the PMOS is open. So you set the output U equal to A, and in the vice versa, when S it is equal to 0. And this is a very simple way for realizing a multiplexer function. Okay, so last point to be discussed in this part of the lesson, it is a problem related to power consumption. So after seeing some example of realization of, let's say, a bit more complicated logic function respect to the very simple inverter, we said, okay, now we have a circuit, a digital module. Here inside, we have several transistors realizing many very complicated logic functions, as we learned. Then you have all the PMOS part on the top, and so on. You can have 1,000 or a million of these transistors. The problem is that you have your inputs, your output, and everything is connected to ground and the VDD. How much is the power we need, how much energy we consume for making this circuit working? So we must be able to evaluate and calculate the power consumption. And it is very important to understand where this power consumption is coming from if we want to take design choices for making this circuit fast, or for example, for making this circuit energy efficient. Because an important point, as we will discuss, it's not only the speed, but also the energy required for reaching that particular speed. Okay. We will learn that, of course, the power consumption will depend also on the voltage that we supply. You can understand that, of course, if you work at higher supply voltages, you will consume more power. Why? How we calculate this power we are consuming? Let's start from a simple example. This is our very complicated digital module. We focus only on one stage. As usual, the simplest, the totem pole stage. What we have? We have that this is our module. And as we learned today, when you have the output of your digital circuit and you want to input it to another digital module, so this the problem is this one. You have this digital module. You take the output and you connect this output to another module, another digital module. This is module A, this is module 1. both can be very complicated. We learned today that since the input of any digital module is always a gate of transistor, because we learn that even if you realize very complicated combinational logic functions, these combinational logic functions, they are always given by PMOS and NMOS that enters in series in parallel. The conclusion that we just learned, it is that the input, these input, they are always gates, right, of MOS. So in conclusion, we know that the input current, how much is it always? How much is always this input current? 0. This input current is always basically 0 because it's always the current entering into a gate of a transistor, so it's 0. The current is 0, but we learn that if we look in this direction, what we see it is the input capacitance of this module, right? So what we have? We have that when you work in a steady state, so when, for example, you have this output voltage high, do you have current here? Is there any current? Hey guys, there, do you have current flowing here? If we say not during the transient, when you are already past the transient, when you are in steady state, at T infinite, do you have current? No, there's no current. Then, if we look in this direction inside the driver, the digital module A, what do we have here? The output interface, as we learn, it's always PMOS that allows our the connection to VDD. This is the output. And MOS. This PMOS can be just one PMOS or many that stay in series in parallel. But anyhow, you have PMOS that are connected to VDD and NMOS that are connected to ground. And then you have your output. When you have this condition, output high, what we have? We have that the PMOS are closed and the NMOS are open. As we learned several times, you can replace this one with an open switch. And you can replace this one with the resistor. So in this steady state condition with output high, do we have power consumption? Are we requiring any kind of energy from the voltage supply? Are we is there a request to the voltage supply of energy? Is there? No, there's not, because the power consumption P is given by current times voltage. The voltage is VDD, but we have no current here. This current is 0 because there's no current flowing, right? So the static power consumption, when the output is high, it is 0 because we do not consume power, because simply we do not have current. Okay, Is this actually true? Is this actually true? This is not actually true because if you remember, the more correct circuit, it is, okay, this one, but okay, but because we have to add here the offset current, because the NMOS, it's not an ideal open circuit, but it has a current leakage. Yeah, so the problem is that we said, okay, we have no, in this configuration, we said there's no current because in steady state, the capacitor is fully charged. There's no current entering in the gate of the MOS. So you can see that the current flowing in this circuit, it is 0. And therefore, the power consumption, the power we request to the voltage supply to make our inverter working, so to make our inverter to stay in the high state, it is 0. So we do not consume any power. This is not actually true because, as we see here, it's true that you have no current here in this direction, but there's a small leakage current flowing from VGG down to ground. So actually the power consumption is I off times VDD. This is extremely small because, as we learned last time, this I off, it is of the order of the nanoampere. So you have nanoampere times volt. In conclusion, this power dissipation for one stage, it is of the order of the nanowatt. So you can basically neglect it, okay? For one. So this is explained here. And this is what happens when, let me go back to the original slides. This is what happens when we are in steady state. So in steady state, we have no current flow between VGG and ground, a part of the small leakage current. And therefore, we say, okay, static current is 0, and static power dissipation is basically 0. And this is the explanation that we have here. What happens during the transient? So the dynamic power consumption, it is defined as the power we need for switching the output. So it is the power that we consume during the transient. Is this power 0 during the transient? No. Why? Why is this not 0? Do we have a current flow? Yes, during the transient, we do have current flow because during the transient, we need to charge or discharge the capacitor. Let's assume, as shown in this figure, in this slide here, that we have a transient of this output from low to high state. During the transient, we are charging the capacitor with a current indicated here in green, and this is the charging current which is provided by the voltage supply. So during this transient, we take current from the voltage supply to charge, so to guarantee to the output our high state. During the opposite transient, so from high to low, this current that we use to charge this capacitor, it is returned to ground via the NMOS. So we have a power consumption during the transient, and this power constant dissipation, it is defined as a dynamic power consumption. Now we want to calculate it. So we want to say how much is this dynamic power consumption? And here it's the demonstration on how we can calculate the dynamic power consumption. So let's do that. Let's consider this transient. PMOS, VDD, capacitor load, which is charged during the transient. When the transient is concluded, so at T infinite, we have that this capacitor will be completely charged to the output voltage equal to VDD. So it means that during this transient from low to high state, we have to accumulate here a quantity of charge, of positive charge on this side. And I indicate this quantity of positive charge such that the output goes to VDD. This quantity of positive charge, by definition of a capacitor, it is equal to C input times VDD. So this is the quantity of charge we are accumulating during the transient. And it is given here. How much is the current? A rough approximation of this current, I remind you that by definition, current is the Q over the T, so the variation of quantity of charge per unit of time. So I can estimate the current during the transient as the quantity of charge that I accumulated divided by the duration delta T of the transient. Let's assume that I have a transition low to high, then another transition high to low, then another transition low to high, and so on. So I charge, discharge, charge, discharge. I have a continuous commutation from high to low, low to high, what is typically is happening in average in a circuit. How fast is this? How often I switch this state? The switch of the state, the speed, is the frequency of the switching, the speed of my circuit, in the sense that I switch with a frequency, with a rate that I indicate with F from low to high, then from high to low, from low to high, and so on and so forth. Of course, the maximum frequency I can work, it is a frequency such that is equal to the time it takes to charge the capacitor. Of course, I cannot work with a frequency higher, otherwise I wouldn't give time enough to the capacitor to be charged. So the highest current that I can have is equal to Q times the operation frequency, F. So as you can see here, the current for the charge variation per unit of time is calculated as F time Q. That is, if you substitute in this expression, you find that the current is equal to F C input times VDD. Then how much is the power, the dynamic power consumption? PD is equal current times voltage VDD. This current, it is equal to F C input VDD, then I have to multiply by VDD. We see that the dynamic power consumption for this transition is equal to F C input times VDD square, right? And this is the power I'm consuming for continuous transition, low to high, high to low, and vice versa. So if I assume that in average, this is the transition rate, I can say that this is the power, dynamic power consumption that is necessary to switch my output at a working frequency at a rate given by this frequency f. So, in conclusion, we see that the dynamic power consumption scales proportionally to what? It is proportional to the working frequency, F. It is proportional to the load capacitor, C, and it scales with VDD square. So you can see that if the voltage supply it is too high, you consume a lot of power. So a good idea is trying to reduce as much as possible the voltage supply while keeping the possibility of distinguishing well high and low states. So this is a direction of the technology. If you want to reduce your power consumption, you must be able to work at lower supply voltages first. Second, you see that there's a direct relation between power consumption and frequency. If you want to operate very fast, you have to accept to increase the power consumption. Okay. If you want to run with a fast car, you have to accept to consume more energy. This is quite obvious. So it's clear that if in a processor you increase the clock frequency, you will scale together the power consumption. So in conclusion, we have seen that we have two different types of power, static and dynamic power. If you consider just one totem pole interface, one totem pole, the static power is basically zero because it is proportional, it's just due to the leakage current of the NMOS and you can neglect it. What is not zero? It is the dynamic power, which scales proportionally to the capacitive load, to the frequency, and as a square of the voltage supply. Is this PS0 in an actual digital module? No, it's not. You will calculate it in the exercise section of Thursday. It's not because you have in a module, you have 1,000 of transistors that are off. So altogether, each of them consumes some power, which is negligible. But if that negligible value is multiplied by 10 to the 6 or 10 to the 9 equal to the number of transistors that are off, then that power is not negligible anymore. For what concerns the dynamic power consumption, we must be careful, because you cannot increase too much this dynamic power. Power consumption, it means that the power that you are consuming will return into it. And so if you do not dissipate the heat well, then you have the problem that the temperature of the circuit will increase. If it increases too much, the circuit cannot work well. So the single component, the single MOS, do not work well. So if you consume too much power, then you also must be able to dissipate the heat. So you must be able to cool down your circuit and keep it to a constant, reasonable temperature to make the circuit working correctly. So in conclusion, which are the common methods for reducing the power consumption? As you read here, you must accept or reduce the working frequency, which means that you have to accept to work at a lower speed, or you can be clever and find algorithms that produce the same result but with a reduced number of operation of switches. Remember that any switch means I need power. So if you reduce the switch of the number of transition, it is better. You have to improve the technology, which means that you have to be able to integrate devices with smaller capacitance, so smaller devices with smaller area, or you must be able to reduce the voltage supply VDD. So, but having as a drawback the reduction of the voltage swing between VOH and VOL. Then finally, these two things, dynamic power and delay, they go together. They are not independent. Why? Because what is determining the maximum speed I can operate? I can operate at a certain maximum speed. What is determining the speed? So what is determining the maximum frequency F max, the maximum rate of variation of my output? Any idea? The charging and discharging time. So as a rule of thumb, roughly, I can say that the maximum speed I can operate is inversely proportional to the delay, or to TP if we indicate this delay as propagation. P stands for propagation delay. So you see that roughly you can say the maximum frequency is the inverse of the delay. I can't work faster than the delay, because every time I have to wait for the delay time, and then I can change the state again. So you see that if you make this assumption, you have that the power that you are dissipating is 1 over Tp times C times VDD square. So if you take the product of the power dissipation, the dynamic power dissipation and the delay, Tp, you see that this product, it is equal to C times VDD square. So we say that this power delay product, it is roughly a constant. In the constant that, in the sense that this constant, it is the voltage supply and the capacitance, the load capacitance C. So the power product delay, it is a constant depending on the technology. This is summarized in this slide. And so it is, let's say, a factor of merit of the technology that I'm using. Okay, because if this power delay product it is small, it is because in the technology the capacitor C is small or the voltage supply VDD can be small. Okay. As a summary of all of that, I want to show you here in conclusion this figure. This figure, it is very well known because it is the trend of the evolution of the microprocessor performances in the last 40 years. What we have? We have that to increase the huge increase of the performance of the processors in terms of speed, in terms of occupation area, and in terms then of number of operations that I can make per unit of time, has been driven by the possibility to improve the technology, in the sense that it is given by the fact that I could scale, reduce the dimension of the transistor, and so within the same area of the device, of the chip, I could integrate always more and more transistor. More transistor, it means more gates, it means more logic operation. And I don't know if you already know, this trend of increase of number of transistors inside the chip versus time over the year, it follows a very well-known law, which is known as the Moore's law, which tells that the number of transistor per unit of area per chip, it doubles every 2 years. And as you can see here, you have a very huge increase of the number of transistors with time. This increase made possible what? Made possible the increase of the operation frequency. And so the number of operations that you can perform per unit of time. And the number, this is the evolution of the clock frequency with time. And as you can see here, this clock frequency increased with time. But then nowadays you see it's saturating. So it means that it has reached a maximum. You can no more increase the performance by increasing the clock frequency. Because if you increase the clock frequency further, it means that you have to dissipate more power. Dissipating more power, it means that the dissipation unit is more and more complicated, and there's a limit of the maximum power that you can dissipate easily. So if you want to improve the performance of your processor, instead of using one core, the other solution is, okay, I cannot increase the number of, I cannot increase the performance by increasing the clock frequency, so I will increase the number of cores of processing unit. Okay? And also here you can see that together with the increase of the clock frequency, you have also the increase of the power that you have to dissipate, that is reaching now hundreds of watts. Okay. So what's the trend that you can read here? The trend is that at a certain point, maybe this Moore law will stop, because it's already seen, because you cannot increase forever the clock frequency, you cannot increase further the power consumption, and also you cannot increase further the number of transistors, because to increase further the number of transistors, it means that the transistor will get smaller, 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 smaller. When the length, the size of the transistor is too small, you cannot say you are in the classical regime. Quantum effects will become important. What will happen here, we do not know, or at least people are already working on that. And all this trend can be simply understood. What is nice, that all this trend can be simply understood by this very simple equation. Is there any question? The upper limit of the frequency, it's already there. You can read it here. It is about, now we are at 2.5 gigahertz or something like that. Yeah, if you read it here, this is 10 to the 3 megahertz. You are a bit farther, it's about to the 2.5 gigahertz. It's difficult to go faster than this. And indeed, it's the actual frequency of the processors. Other questions? Okay, so if there's no other question, I would conclude this lesson here. Next Thursday, you will have exercise section. I will upload now, just after the lesson, the text of the problems and exercise you will solve during that lesson, such that you can have a look before, and if you have time, you can try to solve them. And I will also upload a short notice about the formation of the laboratory groups. So if you want to attend the laboratory, I strongly suggest you to work in groups together with your colleagues, such that you can exchange information, of you can discuss. Each group will have its own breakout room, so you will have your own room where you can work with other students of your group, and I will prepare at least a file where you can register, where you can put your name for each group. Okay, questions?